We know what the universe looks like today, and we have a pretty good idea how it started. With the Big Bang. But what happened in the 14 billion years between the Big Bang and now? How did galaxies, like our Milky Way, evolve? To test our theories, scientists at MIT have built a computer model of the universe. A simulation so complex that calculating it on a single desktop would take 2,000 years. They modelled a volume of space almost 350 million light-years across, a large enough chunk to be representative of the whole universe, but detailed enough to delve into individual galaxies, a feat no other team has managed. The model doesn't just tackle the universe's huge range of scales. It also richly describes the forces at work, much better than previous attempts. By factoring in the laws of physics, and a variety of theories about how gases cool, stars evolve and black holes grow, the model recreates both the galaxies and stars we can see, and the dark matter and dark energy that we can't. The simulation starts just 12 million years after the Big Bang, when things start to get interesting. Dark matter clusters together under the force of gravity. If we could see it, it would look like a web. In fact, scientists call it the cosmic web. Where dark matter is densest, shown as bright pink spots, ordinary matter also clumps and forms into galaxies. Now we're looking at the ordinary matter. Blue shows relatively cold clouds of gas, where stars form. Green is warmer gas, while red and white show hot regions around the most violent galaxies. Supermassive black holes grow at the centre of these. As they gobble up matter, they superheat the material around it, blowing out gas in these violent white bursts. Over time, this enriches the space between galaxies with warm but sparse gas. The simulation also shows the distribution of different elements. The early universe was full of helium and hydrogen. As stars evolve and die in supernovae, they fuse these basic chemicals into heavier elements, such as carbon and oxygen, as well as metals. The violent bursts around black holes spread these elements across space, the pink clouds you see here. Life depends on these chemical building blocks. Only when you have enough of them do planets and complex molecules form. We're looking at dark matter again, and we've almost reached the present day. 14 billion years of the universe's evolution has pulled a tightly woven dark matter web into a looser network of giant galaxy clusters. A big challenge, the team say, was recreating the variety of galaxies we observe. The model's 40,000 galaxies include this spiral one, like our Milky Way. In fact, the simulation produces a world that's remarkably similar to the real universe, as we see it through our telescopes. And because the simulation matches our observations so well, it gives us greater confidence in our understanding of the universe. How it began, how galaxies formed, what it's made of, and the laws that govern it. Of course, the model is not perfect, but where it fails, the simulation challenges our view of the universe. It begs the question, if our descriptions don't match what we see, what might we yet be missing?